Hello guys, welcome to Ramta Solutions. Welcome to your grade 11 electric circuits. This is your first video on your grade 12 electric circuits. And without any waste of time, this is what we call the Ohm's law. This is your first introduction to grade 11 circuits. And let me not scare you. You have seen this before. All right. So in this video, we're going to, as is usual, begin with our revising whatever that we learned and is critical for us in grade 11. It's whatever that we learned in grade 10. Then proceed to the order of the day, which is Ohm's law, what the law is about. Okay, we're going to tell you more about this law. We're going to dwell a bit on this law, but it's not really difficult. It's not something that you haven't seen. It's something that you have seen, but you didn't know that you can call it Ohm's law. Okay. Then we conclude this video with worked examples. There might be one or two, honestly. There might be one or two because, to be honest, calculations are what you did in grade 10. We will drop the link of this video. We will drop a link of your grade 10 videos in the description on YouTube. Okay, so let's see. Without any waste of time, let's get into it. Now, for our revision, oh boy, let me begin with the black color. For our revision, we're going to begin our revision first. We're going to look at definitions. It's important that we definitions. The first definition we're going to look at is that of a resistance. Okay, is that of a resistance? I remember we symbolize it with the letter. When we talk resistance, we're basically looking at the measure of how hard it is to push electricity through a circuit element. But to put it easily, you can say it is the ratio of the potential difference to the current. All right? It is a ratio of the potential difference to the current. All right? To the current. So the reason I'm giving you this definition rather than writing the one that says a measure of how hard it is to push electricity through a circuit element is because I want to be consistent with definitions of physical sciences. What are they? Definitions of physical sciences, they basically lead you to your formulas, isn't it? They basically lead you to your formulas, right? Right. So, without any waste of time, we are saying R is basically the ratio of potential difference. Potential difference, we symbolize it with the letter V, and current, we symbolize it with the letter I. Can you see that? That's the beauty of it. But otherwise, resistance is the measure of how hard it is to push electricity through a circuit element. The higher the, you should remember this, that you should look at when you have negligible resistance, current is flowing easily in your circuit. All right. But if you have a higher resistance, current doesn't flow that easily. Hence, when you look at this relationship, you can see that we can say basically the relationship is inversely proportional. So if resistance increases, current decreases. If resistance decreases, current increases. They have an inverse relationship. Increase of one is a decrease of the other, vice versa. Okay, perfect. Now let's look at voltage, which is potential difference. Okay, which is potential difference. So potential difference, we symbolize it with the letter V. And by the way, you can also use the word voltage. It's okay. So when we talk potential difference, we are basically talking work done per unit charge, right? So this is work done per unit charge. Work done per unit charge, isn't it? You can also say it is the energy transfer per unit charge, right? It's the energy transferred per unit charge. So from this definition, we are saying potential difference is work done. symbol is W. Per unit charge, its symbol is Q. And by so saying, we are sorted. This is potential difference. Okay. Now let's define current. Now current, we will define it as the rate at which charge moves past a fixed point in a circuit. So current is symbolized with the letter I. So what is this? This is the rate at which, we said it's the rate at which charge moves past a fixed point. Past a fixed point in a circuit element, or in a circuit. Past a fixed point in a circuit. Let me not say in a circuit element. In a circuit. So, whenever you see the word rate, you must know that you are dividing by time. So, the rate at which charge moves. What is charge? Charge is Q. So you can say current is Q over T. It's also okay to say delta T. Nothing wrong with that. Okay? Current is Q over T. Now, let me remind you, a unit that measures current is ammeter. On your circuit, you will see it in this symbol. Okay? You will see it in this symbol. And don't forget that current is measured in ampere. Alright? It's measured in ampere, capital A. Then, a device that measures potential difference is a voltmeter. In a circuit, you see it with this symbol. Okay? And remember, it's measured in volts. Then, we have resistance. Resistance, we see it with this symbol or this symbol. Okay? And of course, it's measured in ohm. Ohm, which we write as letter or symbol omega. Okay? Which we write with symbol omega. So symbol, and we say, unit, not symbol. So unit is ohm, and ohm is written like this, as omega, okay, which we call ohm. Okay? Alright, guys. So this is all that we know. These are all the definitions that we know. However, there's a definition I didn't include here. Which is what we term EMF. EMF is basically work done per unit charge. Okay? But hold on. It's work done per unit charge that a battery can supply. Okay? It's work done per unit charge that a battery can supply. The reason I'm not detailing EMF is because right now in grade 11, you are told that internal resistance is negligible. So basically, whatever load that is, whatever potential difference that is in the external of your circuit is equal to the same potential difference that is supplied by the battery. Okay? So I'm not going to dwell much on EMF, but if you need to know what EMF is, it is work done per unit charge that a battery can supply. Okay? Work done per unit charge that a battery can supply. Alright. Now, the second part of our revision, we're going to look at resistor connections. Okay, we're going to look at the resistor connections. I'm not going to dwell much on this, but it's a reminder which to me is very important that you guys know this. So we begin with a series connection. Okay, we begin with series connection. So for our series connection, let's imagine having a circuit like this. Let me start with a positive terminal. And let's say this is your ammeter. And let's say this is your resistor 1. This is your resistor 2. This is your resistor 3. And let's also say this is your voltage. Okay. Okay. So now when we look at this, first, we need to look at the direction in which current is flowing. first thing first, current is flowing from the positive terminal. So from the positive terminal, it goes outwards. So here is your current. Now, for you to know whether current, it's important to know first thing first, whether current is divided on. Current, if there are no joints in your conductors, okay, in your connecting wires, if there are no joints, you must know that current is not divided. So in other words, total current, which is one that flows from the battery, will be equal to current that's flowing in resistor 1, will be equal to current that's flowing in resistor 2, will be equal to current that's flowing in resistor 3, and so on if you have more than 3 resistors. Okay, if you have more than 3 resistors. Okay, so now by saying current is not divided, this means that potential difference must be divided. So the total potential difference will be equal to the potential difference of each component. So potential difference of resistor 1, potential difference plus potential difference of resistor 2, plus potential difference of resistor 3, and so on. Okay, now by saying that, if you are to substitute on this equation, if you are to substitute, remember R, let me remind you, remember R is equal to V over I. Now, if you say V is equal to IR, if you are to substitute I into this, you will get that the total resistance is, what is it? The total resistance, let me call it RS for resistors in series, is R sub 1 plus R sub 2 plus R sub 3. And so on. Okay, now this comes to a conclusion that resistors in series, what are they? They're not current dividers, but they potential difference dividers. All right, you can call them potential dividers or potential difference dividers. Okay, so we're going to call them potential difference dividers. Okay, potential difference, oh my. So we're going to call them potential difference dividers. Okay, potential difference dividers, or simply potential dividers. Why did I say that? I mean, current is not split, but potential difference is split amongst the resistors connected in series. Okay, this is what we need to know. Okay, it's important. Proceeding, let's then look at 1.2.2 parallel connection. Parallel connection. Parallel connection will be, let's see, I'm going to start with a small, large, small, big, just like that. And I don't have to put a letter that side. I can put it here. Okay, so we will say this is R sub 1, R sub 2, R sub 3. Okay. There you are. So now, oh, and there's also a voltmeter there. Let me just put a voltmeter here. So in which direction is current flowing? Remember, current flows from the positive terminal. So it flows in this way. So what we need to know, the current that's flowing here is what we term the total current. It's this current that's here will be registered by this device, right? So the total current, as you can see, current, remember, current gets split across a joint. So when your current gets here, it gets split, right? We will call this part here 1, this one here 2, and this one here 3. Okay. So what are we saying? We are saying if we say current is divided first and first, this means total current is equal to current flowing at resistor 1 plus current flowing at resistor 2 plus current flowing at resistor 3, and so on. Okay? Now, what does that mean? This means if current is divided, it means potential difference is not divided. So potential difference is the same. So total potential difference is equal to the potential difference at resistor 1, is equal to the potential difference at resistor 2, is equal to the potential difference at resistor 3, and so on. But you will be limited to a maximum of 3. Okay, this part, guys, this part, we can call it VP if you like. Okay, we can call it VP if you like. All right, so basically saying, oh, this could therefore be total potential difference. When you have a connection like this, is basically equal to V sub P. Okay, I don't like it when we write it like this, because it means you have VP. But when you say V sub P, it makes sense now, right? Because when you say VP, it's like you have voltage and P for power, maybe, or P for something else, right? So now, by having said that, we can then conclude, if we substitute these into these guys here, right? Not necessarily these, but if we substitute let me remind you, R is equal to V over I. Now, if we say I is equal to V over R, we are going to find that what we term 1 over RP will be equal to 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3 plus and so on. Okay, so 1 over R sub P. This R sub P is to say resistors in parallel. Okay, is to say R in resistors in parallel. Okay, remember, this is not your resistance in parallel. It's 1 over RP. Whatever answer that you will get, to get RP, you need to invert it. Okay, you need to invert it. Okay, you need to invert it. All right, so now this therefore tells us that parallel connection, what is it? It is a current divider. Right? It is a current divider. Can you guys see that? Current is divided for resistors in parallel, but potential difference is divided, and potential difference is divided in resistors connected in series. Right? Potential difference is divided here for resistors connected in series, but current is the same. Now, for parallel connection, current is divided, but potential difference. Note this difference, okay? So without any waste of time, let's then proceed to the next item. The next item is item 2. Item 2 is Ohm's law. Item 2 is Ohm's law. Okay? So this describes the relationship between current and potential difference. Between current and the potential difference. Okay? It describes the relationship between current and the potential difference. Okay? So, it was discovered by this, I think he's German, if not German, Dutch, whatever. But let me not say whatever. It was discovered by this German mathematician. Yes, he's German. It was discovered by this German mathematician and physicist. So it was discovered by this mathematician and physicist by the name George without an E. George Simon. But because he's German, we shouldn't say Simon, we should say Simon, eh? So George without an E. Sorry, Mr. George. So it was discovered by George without an E, Simon Ohm. Okay, it was discovered by George without an E, Simon Ohm. Okay, Mr. George Simon Ohm is the one that discovered the relationship between current and the potential difference. So his discovery was that, so in other words, Ohm's law states. Okay, so this law is named after him. The law states what? The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. I'm going to write it. Okay. Potential difference in a conductor, across, let me use the word across. It looks so serious when I say across. The potential difference across a conductor across a conductor is directly proportional. Right? It's directly proportional. Is directly proportional to the current in the conductor at constant temperature. All right? At constant temperature. At constant temperature. Right? So, if we say it describes the relationship between current and the potential difference. But what did he discover? He discovered that, in fact, this relationship is directly proportional. All right? So mathematically, we are saying, remember, potential difference has the symbol V, is directly proportional to current with the symbol I. Now, guys, you are in grade 11. In grade 10 mathematics, you spoke about indirect proportionality and direct proportionality. You said if quantities are directly proportional, right? If they are directly proportional, their ratio is constant. So what we can say, it's up to you guys. You can say K is going to be a constant. K is equal to I over V. Or you can say V over I is equal to K. It's totally up to you. I'm going to come back to these guys because there's really something that I need to show you. The meaning of these K's are different. You have to understand what it means, okay? Coming back. So now, the experiment or the experimental results, let me put them like that. The experimental results of Mr. Ohm, of George, without an E, Simon Ohm, were drawn, okay, they were drawn as current, were drawn as current versus V. The following was observed. The following was observed. Right? The following was observed. Highlight this, guys. Current versus V. So this is your current. Here is it. Current in what? Amperes. And voltage in what? Volts. What did you do is like this. In fact, this is super small. Let me make it a bit longer. It's better this way. Yeah, it's better this way. Current in ampere and voltage in volts. So the results were a straight line, right? The results were a straight line, right? The results were a straight line. Remember, for quantities to be directly proportional, they must vary in a straight line, okay? So since this is a straight line, there is what we term a slope. And the slope is a ratio of vertical distance over ratio of horizontal distance or horizontal difference. So the slope, which you call gradient, let me be consistent. Those that are doing geography, you call it slope. And those that are not doing geography, let's just stick to gradient. When you talk gradient, it will be delta I over delta V, isn't it? Vertical difference over horizontal difference. This is the gradient. And this is what Ohm's law was saying, right? So it says that there will be a gradient, right? And remember, gradient between 2 points is the same in as whatever gradient along the line. Whichever 2 points you choose, the gradient will always be the same. Okay? So now, what do we have? So this quantity, we have seen it before. Remember, in our opening slide, we said, what was resistance. It was potential difference over current. But look at this. Look at this. This is current over potential difference. Therefore, this means this must be 1 over resistance. So 1 over resistance is delta I over delta V. This is what your exam will ask you. So this particular part here is 1 over R is equal to I over V. I think they call it resistivity, something like that. This, as you can see, it's V over R. What do you know it to be? You know it to be resistance. So V over I is R. So be careful, guys, what you are having in your experiment. Normally, this section, they give you a graph like this. Okay? Normally, in this section, they give you a graph like this. Okay? They give you a graph like this, and they ask you, what is the slope? What does the slope represent? Be careful. If you are given I versus V, the slope does not represent gradient, but rather it represents 1 over R, which we refer to as resistivity. Okay? Resistivity, yes, resistivity. Okay? This will be resistivity, but you don't deal with that. So just call it 1 over R. Okay? But for knowledge base, just call it 1 over R. But for knowledge base, you must know that it's resistivity. Okay? It's what we call resistivity. All right. Now, let's then proceed. Oh boy, what has happened now? Okay, now let's proceed. Then we are going to look at ohmic and non-ohmic conductors. Let me see how I should introduce that. Okay, ohmic and non-ohmic conductors. Okay, so I'm going to call it 2.1, ohmic and non-ohmic conductors. Ohmic and non-ohmic conductors. You will be asked for these differences. Okay, so for a conductor to say it's ohmic, it must obey the Ohm's law. So I'm going to put this in a table. Let's say ohmic conductor. Okay, it's going to be ohmic conductor versus non-ohmic conductor. Non-ohmic conductor. Okay. Now, an ohmic conductor obeys Ohm's law. Right? Obeys Ohm's law. This one does not obey Ohm's law. Does not obey Ohm's law. Right? Now, what I want to say here is that this one here, it has constant resistance. It's important that I mention that. Constant resistance. This one here does not have constant resistance. Okay, does not have constant resistance. Does not have constant resistance. And I think for this, I should also say that temperature is constant. I should say temperature is constant. Maybe it's better. So temperature is constant. So temperature is constant. For this one, temperature is not constant. Right? For this one, temperature is not constant. Is not constant. Right? Now, I versus V is a straight line. So I versus V is a straight line. Okay? And for this one, I versus V is not straight. I versus V is a straight line. This I versus V is non-straight. Non-straight, I mean not a straight line. So it'll be something like this. Okay, this is I, this is V. This is I, this is V. Okay. Now, guys, remember, Ohm's law, it says current or potential difference is directly proportional to current, provided temperature is constant, right? So conductors that are obeying Ohm's law, their temperature will be constant. I'm going to give you examples and you will see that. You will see that. Now, we are continuing. So, examples. Think of your copper wires, silver wires, and so on. All right? Copper wires, silver wires. Okay? And then, for this one, I want you to think of light. Okay? Think of light bulbs. If you are like me, you change your own light bulb, you will realize that I can change it when it's still out. You'll realize that whenever you touch that bulb, I'm saying light wires, light bulb, whenever you change that bulb, when it's still on, even if you switch it off, guys, you'll realize that it's very hot, all right? You'll realize that it's very hot. So remember, when it says it's very hot, it means temperature is increasing. And for temperature to increase, it's not constant. And therefore, it means it does not obey Ohm's law, right? It does not obey Ohm's law. So light bulbs, right? Diodes, right? Light bulbs, diodes, transistors as well. Transistors, and so on. Okay, and so on. Okay, so these are examples that we have. Oh, and by the way, here I can also try nichrome wires as well. Okay, I can also try nichrome wires, right? So these are the things that tell us that, oh, you obey Ohm's law and you don't obey Ohm's law. But the difference is this. Your temperature is increasing, so you get heated. So if whatever appliance you using gets heated whenever it's being in use or it's in use, it means that it doesn't obey Ohm's law. Its conductor does not obey Ohm's law. All right? When it obeys Ohm's law, its temperature will be constant. Okay? Perfect. So we are done with Ohm's law. Now let's get to some worked examples. Let's get to worked examples. This is the third part of our video. So we're looking at worked examples. So worked examples. Now, I think I should give you only one because really the calculations of R equals V over I is what we know. So let's look at this. I'm going to say, for example, given the following. So given the following, when I say voltage, let me say voltage plus V, and current cos I, and the values are 3.0, 6.0, 9.0, and 12.0. For current, you have 0.4, 0.8, 1.2, 1.6. Question 1. Plot I versus V. Okay? Question 1. Let me call it Roman figure 1. Plot I versus. Okay? Going to the next page. Roman figure 2. What is the gradient? Should I add? Okay. What is the gradient of the graph? If it exists. If it exists. Okay? If it exists. Okay, if it exists. And then Roman figure 3, do these results verify Ohm's law? Do these results verify Ohm's law? Okay, that's the question that you should ask. Oh, I'm asking. So let's go look at them. We need to draw a nice graph for these, okay? So we're going to do that. I'm gonna add a grid. Let me see, I think I can do that here. Let me add a grid, guys. And then I'm gonna add a grid, and then I'm gonna draw some nice lines. Let's see that grid. I'll need, okay, I think it'll work. Oh, I think it'll work. And then okay, so let's see. So this is, let's see, we are drawing current versus I. So current, let me remove this for now. So current 0.4 to 1.6. So let me begin with 4, 8, 12. Okay, 1.6, 1.2, 0.8, 0.4. Now, potential difference was what? 3. So it varies 3, 6, 9, 12. Let me reduce this line. Too long. It's fine. Okay, so this is potential difference measuring volts. So when potential difference is 3, voltage was 0.4. When potential difference is 6, voltage was 0.8. When it was 9, voltage was 1.2. When it was 12, current was 1.6 volt. So if you were to draw a straight line between them, this is what you would realize, right? You would see that, can you see that? Can you see that? These are our solutions, by the way. Let me remove the grid. I'm done with it. Besides, I don't like it. So these are our solutions, right? These are our solutions. So Roman figure 1, this is our solution, right? So we drew the graph. Now, since we drew the graph, you can see that I versus V is a straight line. This already answers question 3 that says it verifies Ohm's law, right? Because these are varying. What is this? They are, how can I put it? I shouldn't be saying they are varying, but the line is a straight line. Now, since the line is a straight line, it says to us Ohm's law is verified. But I'm also going to show you another thing. So, now, question 2, what is the gradient of the graph? The gradient of the graph, what is it? I'm not going to stress much about it. Gradient of the graph is delta I over delta V. This is the definition of gradient that we know from maths. Okay, delta I over delta V. So we take gradient between 2 points. We're going to take this point here and this point here. Even if you take this point and this point, or this point and this point, you will get the same. Okay, so what is it? It's 0.8 minus 0.4. What is it? V, it's 6 minus 3. What do we get? Let's see. I'm going to write it correct to 2 decimal places. Our answer will be correct to 2 decimal places. So it's 0.4 over 3. Oh, this is 0.13. Okay? This is 0.13. Remember, guys, this quantity does not represent resistance. It represents 1 over R. So question 3, do these results verify Ohm's law? Yes. The question, why? Maybe I should also add this explain. Okay, explain. Yes. Why? Why? I versus V is a straight line. As simple as that. Right? I versus V is a straight line. Okay? As simple as that. Okay? Perfect. Now, here's another way that I would like us to confirm. I'm going to add this here. I'm going to say I over V. Let's see. What is I over V? 0.4, 0.4 over 3. What is it? It's 0.13. 0.13. 0.8 over 6. What is it? It's 0.13. It's 0.13. 1.2 over 9. What is it? It's 0.13. 16 over 12. What is it? It's 0.13. Oh, sorry, not 16. 1.3. 1.6 over 12. Sorry, my mistake. 1.6 over 12. It's 0.13. So as you can see, when quantities are directly proportional, their ratio will be a constant. Can you see this? These are directly proportional. Their ratios are constant. Can you see this? This is constant. So indeed, Ohm's law is verified. Okay? Ohm's law is verified. So you can verify Ohm's law by drawing a graph, or you can verify Ohm's law by plotting, drawing these values. Okay? If you get this, you must know that Ohm's law is verified. Okay? So this is it, guys. But before we proceed, I want to make sure that I emphasize this point very well. I know some are saying, "You're grade 9, say it's a long time ago." Guys, if quantities are directly proportional, their ratios, meaning something over something, will be constant. Okay? And if they are indirectly proportional, their product will be constant. That you will see later when we do ideal guesses. Okay? So for now, because this one says they are directly proportional, their ratio will be a constant. So I want to say, guys, this thing here is a constant. Okay? This thing here is a constant. Okay? This thing here is a constant. Okay? And with our work, the example that we did, you can see that indeed it's a constant. So this verifies what we said. Resistance is constant for an ohmic conductor. Happy? Great. Now, remember, guys, if you are interested in working with us, say you're looking for a tutor, you can get in touch with us on our website, www.ramtasolutions.co.za. You can go to get a tutor page and you will be directed, or you will be required to fill a form. After filling that form, make sure that your parents know that you want a tutor, and we will communicate with your parents so that we talk about how our program works and how it can benefit you. And of course, if you'd like to communicate with us anything, you can follow us because you're watching this video on YouTube. You can subscribe, comment, or if you like, you can chat to us on WhatsApp. You can follow us on your favorite social media, Twitter, Facebook. Oh, Twitter, we call it X, Facebook, Instagram, and all this. Okay. Otherwise, you can also you can email us. Talk to us via email. We will be glad to assist you. You can also, on the very same website, you can go to the blog page. In the blog page, there are various articles that we have uploaded that you can read, that you can study with as well. Some of the topics are there explained in the blog post. Okay, so this is it, guys. With that said, ours ends here and it's a wrap. So, bye-bye.